Welcome to The Explainer. Today, we're going to pull back the curtain and decode the invisible signals that pretty much run our entire modern world.
Right, we're diving into the world of industrial network protocols. I know, it sounds technical, but these are basically the secret languages that let massive, complex systems coordinate with each other, totally flawlessly.
So here's our game plan for this explainer. We're going to start on the factory floor, get to know the languages, see who the big dogs are in the market, and then we're going to connect it all back to the internet and break down piece by piece how a bit of data gets from point A to point B.
Okay, first things first. Before any machine can even think about talking to another one, they have to agree on the rules of the conversation. And that's exactly what a protocol is. It's just a shared language. It doesn't matter if it's a giant robotic arm, a tiny pressure sensor, or the brain of the operation, the PLC. They all have to speak the same dialect to get anything done. Inside what we call an operational technology, or OT network, everybody speaks the same language, period.
So, now that we know what these protocols are, let's take a look at the biggest players out there. I mean, while there are a ton of these languages, two of them have really become the titans of the industry. And here they are. You've got Ethernet/IP and Profinet. Together, they command a whopping 60% of the entire market. So, if you want to understand modern industry, you've really got to understand these two. First up, Ethernet/IP. Now, right off the bat, let's clear something up. The IP here, it actually stands for Industrial Protocol, not Internet Protocol. It's a huge force, especially in the US, and its biggest advantage is that it's built on standard stuff we already use for the Internet. This makes connecting the factory floor to the main office network an absolute breeze.
And on the other side of the ring, you've got Profinet. It's super popular in Europe. Now, Profinet is all about one thing: speed and predictable performance. Think of it like a perfectly timed orchestra. It comes in different flavors, too. You have the standard speed, a faster real-time tier for quick responses, and then there's isochronous real-time, or IRT. That is just blisteringly fast. We're talking precise enough for the most complex robotics you can imagine. But, it's not just a two-horse race. Outside of those big two, there's this whole world of other more specialized protocols. Each one is designed and fine-tuned for a very, very specific job.
For instance, you've got Modbus. It's one of the oldest and simplest out there, a real workhorse. Then there's DMP3, which is the specific language that runs our public power and water grids. And then inside the building you're in right now, chances are BACnet is the protocol keeping the AC, the lights, and the fire alarms all working together. Okay, so we have all these specialized languages on the factory floor, but how in the world do they talk to the front office, to the business side of things? How do they connect to the rest of the internet?
And the answer is something you use every single day: TCP/IP. It's the granddaddy of them all, the protocol that basically holds the entire internet together. By wrapping up their unique data inside a TCP/IP package, these industrial networks can talk to pretty much any other computer system on the planet. It's the universal translator.
So, how does that whole packaging process actually work? Well, any information, whether it's an email or a reading from a sensor, gets chopped up and sent in these tiny little bundles called packets.
The easiest way to think of a TCP/IP packet is like a digital envelope. The IP header? That's the address on the outside. It says where it's from and where it's going. The TCP header is kind of like the instructions inside for certified mail, making sure it gets delivered properly. And the payload? Well, that's the actual letter, the data you're trying to send.
So the IP header is the basic stuff, the mailing label. It clearly states the source and destination addresses as a string of numbers. But it also has this really clever feature called time to live. It's basically a self-destruct counter that stops lost packets from just bouncing around the internet forever.
Now the TCP header, that's where the real magic, the quality control happens. The port number, think of that like an apartment number. It makes sure the data goes to the right program, web traffic here, email over there. The sequence number is like numbering the pages of a long letter so they can all be put back in the right order. And the acknowledgement number is the system's way of saying, okay, got page 1, go ahead and send page 2. And this just shows the whole journey beautifully. A big chunk of data leaves one computer, it gets chopped up by routers to travel more easily across all these different networks, and then all those tiny pieces arrive at the destination, where they are seamlessly put back together in the exact right order. It is an incredible ballet of coordination that happens billions of times every single second. But wait a minute, we don't type in a bunch of numbers to visit a website, right? We use a name, like Google.com.
So how does the network translate that human-friendly name into the long numerical IP address that the machines actually need?
For that, we need the Domain Name System, or DNS. Honestly, you can just think of it as the Internet's giant shared phone book. Its one and only job is to look up the names we use and find the numbers the network needs.
And this all happens through a super fast, hierarchical search. Your computer asks your local DNS server. If it doesn't know, it asks a root server. The root server points it to the right top-level domain, like the server for all .com addresses. That server then points to the specific website server, which finally hands over the IP address. This whole chain reaction happens in the blink of an eye.
Now, as you can imagine, managing all of these addresses by hand would be a nightmare. And that's where a related protocol comes in, DHCP, the Dynamic Host Configuration Protocol. This thing is like a network receptionist, just automatically handing out temporary IP addresses to devices as they connect.
And this brings up a really crucial point. While DHCP is a total lifesaver in a regular office or IT network where your laptop's address can change every day and it's no big deal, it can be a serious problem in an OT network. A critical factory controller can't just change its address whenever it feels like it. It needs a permanent, unchanging, static IP address so other systems always know where to find it.
You know, at the end of the day, it really all boils down to this one question. What's the best protocol? It's the one that's supported by the gear you need to do the job. It's all about making sure everything can speak the same language, loud and clear.
And that leads us to our final thought for today. This massive convergence of industrial tech and internet tech, it has unlocked some unbelievable efficiencies. But, and this is a big but, it has also exposed systems that were built to be isolated and reliable to a whole new world of global cyber threats. Figuring out how to secure this new, hyper-connected industrial world, well, that's one of the biggest challenges we're facing right now.